Okay, let's look at some example problems. So which of these graphs is the most appropriate model for the temperature of a city on a particular day? Explain your reasoning. Time is measured in hours after midnight. Okay, so this 0 on our x-axis is midnight. So, and then 24 hours later, that's midnight again. Now, let's look at B. This is the worst model. What this is saying, if we look at B, is it starts out at 10 degrees and it keeps going up, 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 up from from midnight to midnight. It keeps going up. Temperature keeps increasing, increasing, increasing. We know that's not how temperature works. Um, we know the temperature goes up and down throughout the day. So let's look at these two models. This first one here, this one we're starting at midnight and then it's saying, okay, temperature is going up from midnight. And then at about 6 a.m., that would be the highest temperature. And then it starts falling and until about 6 p.m. and then it starts rising again. We know that's typically not how a day works. We know the daylight hours, because of the sun rising, is when it's warmest, and then nighttime is when the sun's down. So that's when it's the coolest, and that's what this one shows. So we were at midnight, keeps getting colder and colder until the sun rises at about 6, increases, and then drops again. So C is the best model of this. And then number B asks us to use the model to predict the temperature at 8 p.m. So 8 p.m., that's noon plus 8 hours. So if we're doing 24-hour time, that's 2000 hours, and which is like maybe about right there. That's about H equals 20. And so we look up, we see it's about 28 degrees Celsius. Corey, what did they say 30 degrees on Celsius was on British Bake Off the other day? You did the calculation. Okay, so they said, we were watching British Baking Show, and they were like, oh my gosh, it's so hot, it's 30 degrees Celsius in the tent. And Corey looks it up, it was 82 degrees. So, 86 degrees. Anyway, so just help. So watch British Baking Show to help you learn Celsius conversions. Let's look at this other one. It says Antonio's swimming at A, so Antonio's right here, and his belongings are at B, and he gets cold, so he wants to know what's the fastest way to get back to his belongings. Now, this is kind of embarrassing, but this is the kind of problems I do in my head all the time. I kind of create mathematical models like this. Maybe not, I definitely can't swim as fast as Antonio. But find the time it would take to return to his belongings by swimming directly to B. So going from here to B. So we're not given that distance, so we're going to have to use the Pythagorean theorem to do that. So we got 40 squared plus 100 squared is equal to that distance squared. So 40 squared is 1600, 100 squared is 10,000, plus d squared. Add those together, we get 11,600, and that's going to be d squared. I'm going to go to my calculator, because I definitely cannot do that in my head. The square root, and so d is approximately 107.7 meters. And so if he can swim 1.5 meters per second, we want to know how many seconds it is. We need to know how many times 1.5 goes into that. So for part I, we would say 107.7 divided by 1.5. That's meters per second. And when we do that with our calculator, we got 107.7 divided by 1.5 and 71.8 seconds. That's pretty fast to me. It seems like that's very fast to be able to swim 100 meters in a little over a minute, but like I said, Antonio's a better swimmer than me. Let's do part 2 and swimming to C. So that would be 40 meters divided by 1.5, and then you got to jog that last 100 meters, and that's divided by 4. So 40 meters divided by 1.5 is 40 divided by 1.5 is 26.6. 100 divided by 4 is 25 seconds. So we add those together and we're at 51.6 seconds approximately to do that way. So any assumptions, we got to state any assumptions. One is that, he can run or jog at a constant rate. That's one assumption. He's not going to slow down, like as he starts getting tired. Like I know if I swim 100 meters, I would get tired towards the end. There's no current in the water, no wind resistance. Those are kind of assumptions that we're making. And it's that second one that seemed to be quicker. Um, that uh, and so up swimming to the shore than jogging. That seems to be the quickest. Number C, can you find another option that is even quicker? I think we might explore this a little bit in class. So anyway, we might come back to this question in class. All right, y'all. Good luck.